To introduce the next key concept in calculus, let's go back to the example I cited before about driving down to my grandparents' house. But I want to look at it from perhaps an unusual perspective, and that is ask what the speedometer looks like while I'm driving on this trip. So what I'd like to do is I'd like to draw a graph, but with different axes this time. We'll still use time and hours for the x-axis, but since we want to model the speedometer and what's happening to the speedometer, we're just going to make the y-axis the speed in miles per hour. So if you'll recall, we had three different example trips. And the first one was the simplest, where I simply started out early some morning and drove straight at a constant speed. That's how we'll model that. Now I want to ask a question about what the area is that's contained in that rectangle. Well, it's 60 mile per hour units multiplied by 3 hour units. So the area is just, of course, the width times the height of that rectangle, which is 60 miles per hour times 3 hours. So what are the units of that area? And I say area in quotes because the units are obviously not area units. Okay. Well, if you see that the hours cancel out, then what we have is 180 miles. And so on this kind of graph, this area underneath the speed function, in fact, seems to suggest that it gives us the distance traveled. Interesting. So let's recall the second case that we looked at, one where the speed changed a couple of times over the course of the trip. Initially, we drove at 60 miles an hour for the first hour. Then we ran into traffic or rain or whatever excuse we made up to justify saying that we then traveled at 30 miles an hour. And then finally, realizing that we were going to have trouble getting there on time, we did our last leg moving at 90 miles an hour. So the question again is, if we take a look at these distances covered, and I'll connect the dots just to make it look a little more like rectangles, we see that we can model the area underneath the speed function as the area of these three separate rectangles. Well, in each case, it's the width, 1 hour, times the height, 60 miles per hour, plus the width of the second block, which is an hour, times the height, which is 30 miles per hour, and finally the width of that last block, which is an hour, times the height, which is miles per hour. And if we add all those up, we get 180 miles. So again, the distance traveled is the area where area has taken on a broader meaning, because the units of area in this case are miles, where area under the curve is the distance traveled. Well, that leaves us only one more case to look at, and that's the most realistic one. You'll recall that in this third example, the car was driving much more realistically, and as a result, we can expect that the speed was changing continuously. Here's the stop at Wendy's. Sorry for the driving, and then we take off again. Here's when it's time to take the so-called shortcut. Notice that because we were moving backwards, our speed would have been negative. And then finally we really, hate to admit how fast we're going there at the end. But if the two previous examples have told us anything, it suggests that no matter how complex the curve that covers our speed is, that it's still the case that somehow the area under this curve is in fact the distance that we drove and would sum up to 180. But how would we actually do a calculation like that? It was fine when it was a single rectangle. We just multiplied the width times the height. And it even worked when the path, the function that measured speed, was something that could be broken up into 3 separate rectangles. But it doesn't appear that we can make rectangles out of this because of how rapidly the speed function is changing and the fact that it's a continuous curve. Well, what could we do? Well, we could try to make sort of crude rectangles that were approximately the distance that we traveled. And then we take the width of those rectangles and add them up. Take the width multiplied by the height of each rectangle and add them up. And then we would get something like the area. The problem, of course, is that it's not accurate. If you see, for example, this area here, that's not covered by the rectangle, but it's clearly part of the area underneath the curve. Well, is there any way we could make our rectangle approximations more accurate? Well, in fact, there is. We could divide them up into thinner rectangles and more of them. And the question is, if we just make the thickness of our rectangles this, and then we multiply it by a whole series of heights, like this, then if we let the width of the rectangles go all the way down to 0, and the number of rectangles, and therefore the sum of the heights, goes up to infinity, then we get a calculation that should represent the area under the curve exactly, except that it's 0 times infinity. Well, again, we were taught that 0 times infinity was undefined. But I hope I've tried to suggest a rationale for why we need to believe that 0 times infinity in this case is going to again result in the distance that I've driven. A finite number, 180 in this case, 180 miles. And so we're going to give this area under the curve a name. We're going to call it an integral. And that's the second key piece of calculus. Now, if you go back and watch the first video and watch this one again and think about them, you'll sense something that's even more spectacular about calculus, and that is a special formula that connects the first important topic, the derivative, with the integral. I'll leave you that to think about, and if you just can't wait, you can look up the video that covers what's called the fundamental theorem of calculus.